All right, everybody, this is going to be video number 2 for lesson 1 of unit 2. So after we've looked at the basic building blocks of geometry and how to name everything using the appropriate notation, we are now going to look at segments and the segment addition postulate. So first of all, recall that a segment is just a part of a line with two endpoints. So if we're looking at the segment A to B, for example, we can figure out the length of each segment by using a number line. We're also going to look at coordinate plane tomorrow or the next lesson. So in this case, A to B is just the distance on a number line. So it's 1, 2, 3 units away. B to D is just 1, 2, 3, 4 units away. C to D, this segment right here is 1, 2, 3 units away, or units long. And then A to C is 1, 2, 3, 4 units long. Now, one thing to remember about whenever we have a distance or the length of something, it's always positive. You can't go like -2 feet or something like that. You just go 2 feet backwards. It's still like a positive value. So keep in mind that length and distance are always positive. So we can kind of use absolute value to figure out length of units. Now, just a kind of basic breakdown of what the segment addition postulate says is that let's say we wanted to know what A to D is, but we didn't want to count it. We just wanted to use information that we already knew. So A to D is really the same thing as A to C plus C to D. So that's what this segment addition postulate says, is that the length of one segment is the same as adding two segments together that kind of make up that whole segment. So like A to D is the same thing as A to C plus C to D. We know that A to C is 4 units. We know that C to D is 3 units. So we can say that A to D, by using the segment addition postulate here, is actually 7 units long. Instead of just counting is probably faster, but this is an example of what the segment addition postulate says. So just breaking down what the segment addition postulate is, a segment is a part of a line. Addition means we're adding together, so we're adding parts of a line together to make up a whole. And then a postulate is, again, a fancy term that Euclid, the ancient Greek, came up with to basically say that it's a rule or it's a statement that we assume to be true in order to build off of it. There's a lot of postulates in geometry that kind of create the whole world of geometry and allows us to kind of visualize the physical world in general. That's what geometry is being able to make sense of the physical world around us. So the segment addition postulate, this is actually what the theorem says, or the postulate says, is that if you have a line where these 3 points are on the same line, or what they call collinear because they share the same line, if A, B, and C are on the same line with B in the middle, or B in between those 2 points A and C, then we can say that the segment A to B plus the segment B to C is equal to the whole segment A to C. Hopefully the visualization aspect isn't too difficult with this. Again, it's just two segments, saying that two segments added together make up a bigger segment, adding those two together. So let's just look at some examples here real quick. So again, this is just basically what we talked about, where A to D is the same thing as A to C plus C to D. So this is from the last slide. So the best way to, I guess, learn it is to practice it. So example 1, using segment addition postulate. So using the diagram below, we're going to suppose that FH is 26 units long, or the distance from F to H is 26 units. So we want to know what the value of X is. So they use these expressions to represent the length of FG. This expression right here represents the length of G to H. So the first thing that you should do is just set up an equation that represents the length of FH. So again, F to H is this whole segment. It's made up of this segment FG and this segment G to H. So if you add these two segments together, they should equal the whole segment FH. So that's the equation that we come up with. Next, what we can do is we can substitute the expression shown for each of these segments into the equation. So let me plug that, or do that real quick. F to H, they tell us is 26, so that's where the 26 comes from. F to G is represented by this expression 3x minus 1, so that's where that comes from. And G to H is represented by this expression right here, so that's where that comes from. Then, after we have this equation set up, you should notice that we can solve this for x because it has one variable. So that's what step 3 is just solving the equation to figure out what the value of x is. So the first step in solving this equation is simplify this right-hand side over here. We got 3x, so a positive 3x plus a positive 2x. That makes it a positive 5x. We have a negative 1 or a minus 1 plus 2. That makes it a positive 1. 26 doesn't change. Next thing, we're solving for x here, so I'm going to subtract 1 on both sides to get 25 equals 5x. And then 5x is really the same thing as 5 times x. So if we want to get x by itself, we have to divide the 5 out. So x is equal to 25 divided by 5, which is just 5. So if x equals 5, that's our answer. But we could actually take this a step further to see what each of these could be. So f to g, we could take x, plug it in for x. Or take 5, plug it in for x. 3 times 5 is 15. Minus 1 is 14. 5 times 2 is 10. Plus 2 is 12. So those would be your other measurements of our segments here. And then you should notice that f to g is 14. G to h is 12. It doesn't really look like that, but diagrams don't really matter in geometry. What matters are the actual expressions that represent them, because diagrams can be as inaccurate as you want, just so long as the dimensions that you're using or the numbers that you're using represent those. So again, G to H looks a lot longer, but it's actually shorter because that's the way the diagram is drawn. But you should notice that if we take 14 and add it to 12, that should be this whole thing, which is 26, that's what we started with. All right, one other example here. This should help you, again, complete the next 3 problems on the lesson 1 assignment, questions 7, 8, and 9. So using the segment addition postulate here, we have points J, K, L are collinear. That means that they share the same line. If K to L is 43, so they're saying that this little segment, this piece right here, K to L is 43, we want to figure out what the length of J to L is. J to L, this segment JL, is the distance from J to L. So it's really this plus that. It's JK plus KL. So again, step 1, use the given information. So KL is 43. So what we can do is we can actually say that this KL right here, 43, is equal to this expression, because we know that this is the length of it is 43, but it's also the same, it should be equal to whatever this expression is. So that's the setup here, 43 equals 5n minus 7. And we can solve this equation to figure out what n should be. Add 7 to both sides to get 50 equals 5n, and then divide by 5 to get n equals 10. Now we can take the value of n and we can plug it in for wherever we see n to figure out what the segment lengths of J to K and J to L are. So segment addition postulate says that this distance J to L is made up of J to K plus K to L. So if n equals 10, that means that J to K is 3 times 10 is 30. And then we also know that K to L is 43, but again, n is 10, so it's 5 times 10 is 50, minus 7 is 43. So that means that J to L, this whole segment right here, is going to be 30 plus 43, which is 73. So hopefully that breaks down the segment addition postulate. Hopefully it's straightforward, but if you have questions about these problems, let me know. That's how it works, that you should be able to complete problems 7, 8, and 9. And then we have one last video to wrap up angle addition postulate.